now come to the inverse function theorem. The proof of this theorem involves a lot of non-trivial ideas and is probably the longest and toughest of this course. Not only is the theorem and proof hard, it's really useful. All this work will not go to waste. This theorem is extensively used in real analysis as well as other subjects like differential geometry. It's also used in economics, physics, pretty much anywhere multivariable calculus is used, the inverse function theorem is definitely needed. In this course, we will use the inverse function theorem to prove the implicit function theorem, which is really the starting point of the study of manifolds. For the rest of this course, this theorem will keep popping up again and again. As the proof of this theorem is really involved, let me make some remarks about the idea of the proof. The basic idea of the proof is to somehow by hook or crook set up a situation where we can apply Banach's fixed point theorem or the contraction mapping principle. To do this, we will use ideas inspired by Newton's method, but we will not quite use Newton's method or any convergence theorem in Newton's method to prove this theorem. There are proofs available which use Newton's method to prove this. For instance, in Hubbard's textbook on multivariable calculus, this is in fact proved using Newton's method. So, those are some basic remarks. Let's state the theorem. Even the statement of the theorem is a bit involved. So, the setup is f from u to f. U to f is a C1 smooth map, and f of a equal to b, where a is a point in U. Now, the hypothesis, the central hypothesis is, suppose DFA, which is a linear mapping from E to F, suppose DFA is invertible, then we get a number of consequences. Number one is the fact that E is equal to F. This is obvious actually. The fact that a linear mapping is bijective between two vector spaces means that both of them have to be isomorphic, but here E and F are both Euclidean spaces, so they must be the same Rn. We can find open sets V subset of U containing A and W subset of F containing B such that f of A is equal to B. Such that f of A equal to B is already given to us, and W subset of F containing B such that F maps V bijectively onto W. The third part is the most important conclusion. Denoting F restricted to V by G, the map G from W to V is a C1 smooth map, and if G of Y is equal to X, then dg of Y is nothing but dfx inverse. Okay, so this is the statement of the inverse function theorem. Now let's first try to understand intuitively what the theorem is trying to say. Again, the moral of the story is that if a function is differentiable, then the derivative is a good linear approximation of the function. This is something that you would have heard me say at least 568 times in this course. Now, note that we are given that the derivative map dfa is invertible. So as I said, E equal to F comes as an easy consequence because dfa is an isomorphism, therefore F should also be Rn. So since dfa is invertible, the natural conclusion to expect is that F is also invertible, because dfa is a good approximation of F. If dfa is invertible, then naturally we would think that F is invertible. That's the vague, loose idea. But remember that the derivative is an absolutely local thing. The derivative of F at A does not depend on the value of F slightly far away from A, it could be the values of f somewhat far away from A could be entirely different. So expecting that f will be globally invertible just because the derivative is invertible at a single point is a very fool's dream. That's not something that you can expect. In fact, I want you to think of a counter example to the stronger claim that even if DFA is invertible for all points A in U, it's still foolish to expect f to be invertible. Okay? But nevertheless, the conclusion of the inverse function theorem is, at least locally, we can find this open set V around A on which f is just a bijection. Now that's not the end of the story of the inverse function theorem. This inverse map G is not just a set theoretic inverse, it's going to be a C1 smooth map as well. Okay, we will set up some terminology regarding this in the next video, but for the time being, you can think of f being invertible in a differentiable way, and we can compute the derivative at the points y in W. Okay, so this is the basic intuition behind the inverse function theorem. If you have not already done so, I urge you to please watch that short video on the inverse function theorem in one variable, which was actually a part of the previous course on real analysis. Now let's dive into the proof. As I said, there's a lot of work involved in this proof, so let's go full speed ahead. Okay, proof. So I'm going to make some simplifications. First is E equal to F is obvious. Now the simplifications I'm going to make are the following. We are going to assume first of all that A equal to B equal to 0, and second, DFA is the identity matrix. Okay, now I want you to justify these assumptions. Justify that these assumptions are without loss of generality. Okay, what I mean by that is, if you can prove the inverse function theorem in this setting where A equal to B equal to 0 and the derivative map is just the identity, the general result when A is not equal to B and may not be equal to 0 and DFA is just an invertible map and not the identity map, this really doesn't matter. Okay, the general case will follow very easily. Okay, so the first step is to define a new function. Define h of x equal to x minus f of x. Okay, then observe that h is also a C1 map. H is also a C1 smooth map. But the interesting thing is, by our assumptions, dh0 is nothing but identity minus DFA, which is just the 0 map. Okay, so this is the interesting bit. The derivative of h at 0 is nothing but the 0 map. Now we observe that by continuity of dh, we can find a small ball B0R subset of U such that the operator norm of dh of x is less than or equal to half for all x coming from this ball. This follows from the continuity of dh. To understand why this is the case, you will have to understand this coordinate independent formulation of the derivative being continuous, right? We had defined h being C1 just to mean that the partial derivatives exist and are continuous. But in a video earlier, I had also talked about how we can talk about continuity of the derivative map in terms of treating it as a map into the space LEF with the operator norm. So that's the reason why we can find a small ball such that dh at x, the operator norm, will be less than or equal to half for all points. Okay. Now on B0R we have the operator norm of identity minus the derivative of f at x is less than or equal to half. This is just rewriting what the derivative of h at a given point x is. It's just derivative of x minus f of x. It's identity minus df of x. Okay. Now in an earlier example where we studied the derivative of inverses. This is in the context of matrices. We studied this. Matrices and linear mappings are just the same thing represented in different ways. We had studied the derivative of the inverse map on matrices in an earlier example. This was the long involved example. We have already seen that if you have this identity minus dfx op is less than or equal to 1, in fact less than 1, we know that dfx is going to be invertible. We know that dfx is invertible on B0R. Okay, because the operator norm of identity minus dfx is not very large, the invertibility of f continues for all points x in B0R. Okay, now fix x in B0R. We have an estimate about the operator norm of the derivative of h. We know that it's less than or equal to half. So you can apply the mean value theorem and conclude that norm h of x is less than or equal to half norm x. This is just the mean value theorem. Theorem applied on the segment joining 0 to x. Remember, h of 0 is also 0. Okay, so this is just the mean value theorem applied to the segment joining 0 to x. We get that norm hx is less than or equal to half norm x. This just means that h maps the closed ball of radius r into the closed ball of radius r by 2. Okay, we now make a claim if y is an element of B closure r by 2, then there exists unique x in B closure 0 r such that f of x is equal to y. Note, not h of x equal to y, but f of x equal to y. So I am not claiming that f maps B closure 0 r into B closure r by 0 r by 2. H already does that. H takes B closure 0 r into B closure 0 r by 2. But what I am claiming is that if you look at the set of points that are mapped into B closure 0 r by 2, but that which come from B closure 0 r, every single point in B closure 0 r by 2 will be mapped, okay, by f. So the claim is, given y in B closure 0 r by 2, there is a unique point x in B closure 0 r such that f of x equal to y. Okay, so here is the part where we will take our inspiration from Newton's method. So what we want to do is, if y is in B closure 0 R by 2, we need to find x in B closure 0 R such that f of x is equal to y. This is what we want to do. Or we will rewrite this slightly such that f of x minus y is equal to 0. This is what we want to do. Okay. Now Newton's method says start with some x naught in B closure 0 R and try x1 is equal to x naught minus df x naught inverse acting on f of x naught minus y. So here we are fixing y. And we want to find a solution of f of x minus y equal to 0. We want to solve this equation. Newton's method says just start with the guess and look at the better guess x1 equal to x naught minus df x naught inverse f of x naught minus y. Now here we are going to pull a trick. We already know that df0 inverse is going to be equal to the identity, and we also know from what we have considered previously, we also know that this mapping, this derivative identity minus dfx, the operator norm, is less than or equal to half. It's not too far away from being the identity whenever you choose x from this B0R closure. Okay, so what we are going to do is we are going to try our luck, and we are going to simplify this expression by saying we want to guess x1 equal to x naught minus just the identity f of x naught minus y. You might wonder how somebody thought of replacing df x naught inverse by the identity mapping. Well, you will understand in a moment that this actually makes our job really easy. But apart from that, whenever you have a sophisticated theorem, the final proof that you see nowadays is a modern proof that has been obtained over the years. So it's not as if somebody got this without any trial and error or experimentation. A fair bit of experimentation would have happened, and finally just treating dfx naught inverse as just the identity map seems to work. So just hold on for a few minutes. You will see that this is actually a good idea. So once you substitute identity, you get the simplification that x1 is x naught minus fx naught plus y. Again, I remind you that y was fixed. We are trying to find a point x in B0R closure such that f of x is equal to y, and this is our better guess of the solution. We start with an initial guess x naught, and we say the better guess is x naught equal to x naught minus fx naught plus y. So this is just our intuition that comes from Newton's method. Now what we are going to do is we are going to turn this inspiration into a rigorous proof in the following way. So we define a function, we define a function which we call hy. This function starts from B0R closure, and I will just leave the codomain blank for the time moment. This is defined by x maps to y plus x minus f of x, and you can clearly see where the inspiration for this particular choice of function comes from. Okay, now this function has this nice property that if hy of x equal to x, then that just means that y plus x minus f of x equal to x, which just means that f of x equal to y. In other words, a fixed point of hy is precisely the solution we are looking for. The solution to f of x equal to y we are looking for. So we have translated finding the solution to finding a fixed point. This seems promising because just a while back we studied something called the Banach fixed point theorem. So unless this is all happening in a miraculous way, things should work out. Okay. Now let's see what the codomain of this function hy is going to be. Well, to see that, observe that norm y plus x minus f of x is just less than or equal to norm y plus norm h of y. This is not h subscript y, sorry about that. This is norm of h of y. This is just because the function x minus f of x, if you sorry, this is not h of y, this is h of x. H of x. So this just follows because whenever for a given point x, the function h of x is just x minus f of x, and we have just used the triangle inequality. Now note that this point y is also coming from the ball of radius half closure, and h of x is also going to be a point in the ball of radius half closure, simply because we already saw by that mean value theorem that h maps B0R closure inside B0R by 2 closure. So this is less than or equal to half plus half, which is equal to 1. Okay. In other words, this blank that I had left thankfully turns out to be B0R closure. Okay, and the required solution of f of x equal to y is nothing but a fixed point of this map hy. We have a self map, and B closure 0R is a complete metric space being a compact subset of Rn. Therefore, all the parts are in place. We just have to fix it together and apply the Banach fixed point theorem, and all we have to do is to somehow show that this map hy is a contraction. And that's not at all hard. What we have to do is we have to take norm of hy of x1 minus hy of x2, okay, where x1 and x2 come from B0R closure, and you can just check by the formulas that this is nothing but h of x1 minus h of x2. Okay, and this is less than or equal to half of norm x1 minus x2. Okay, so this part just follows by the application of the mean value theorem yet again. Okay, now by the Banach fixed point theorem, we get a unique solution. X in B0R closure. Of course, I have written the closure in an extremely bad way. This is B0R closure for f of x equal to y. Excellent. Okay, so what is the net upshot? We know that f maps or rather, let's write it correctly, every point in B0R by 2 closure has a pre-image under F in B0R closure. Note, we have not shown that this B 0R closure maps into B closure 0R by 2. It could map certain points of B 0R closure outside of B 0R by 2 closure, but at least we get a unique solution for any given point y in B 0R by 2 closure. There is exactly 1x in B 0R closure such that f of x equal to y. Okay, so what we do is the following. We try to find out the set V that we require such that f restricted to V is going to be 1, 1 and on to an open set W in F. That's one of the parts of the inverse function theorem that we have to show. So let's just, since it's been quite some time, let's just look at the statement. We have to find this open set V subset of U containing A and W subset of F containing B such that F maps V bijectively onto W. Okay, so this is our objective. We are going to use this fact that F has solutions in B 0 R by 2 closure to manufacture our V. So define V subset of B 0 R to be the set of points such that so set of points, let's say x, such that f of x is an element of B 0 R by 2. Okay, so we already know that when we consider the collection of all points in B 0 R closure and look at f of that, then you would get a set that is a superset of B 0 R by 2 closure. Now we look at those points in B 0 R which map inside B 0 R by 2. Okay, now observe that V is open. This bit is actually obvious because V is nothing but F inverse of B 0 R by 2, which is an open set because F is continuous, intersect B 0 R to make sure that you don't pick up any points outside B 0 R. So clearly V is open. Set W to be F of V. Right? So first of all, another claim, the second claim of this proof, W is an open set. W is an open set. Okay. Now this claim is somewhat tricky to prove. Let's get to it right away. We know that F from V to W is bijective. Okay, to be 100% precise, I must write F restricted to V from V to W is bijective. This is just the way we manufactured V and W. It's certainly onto because W is F of V. It's certainly injective simply because of the uniqueness part of the previous claim. Okay, now to show that this is an open set, what we are going to do is we are going to consider the inverse already. Let G from W to V be the inverse map. Okay, now our aim is to somehow show that if there is a point such that so if x1 is a point in V and y1 equal to f of x1, okay, our aim is to show that there is an open set around this point y1 which is fully contained in W, or more precisely, if we can find some ball around y1 which is fully contained in W, then we are actually done. Okay, so we have fixed these points x1 in V and y1 is in f of x1. Now by definition, norm of y1 is less than R by 2. Okay, now let y be any other point such that norm y is also less than r by 2. Okay, then we can find by the previous claim, we can find a unique x in B0R closure such that f of x equal to y. Right? Now observe that norm of x minus x1 is less than or equal to norm of h of x plus f of x minus h of x1 minus f of x1. This is just because h of x is defined to be x minus f of x, and there's plenty of cancellations that happen, and this will just drop out. Okay, in fact I believe this is going to be an equality, not even a less than or equal to. So this is less than or equal to norm fx minus fx1, this is by triangle inequality, plus half norm x minus x1, because h is a contraction. We've already seen this is just the application of the mean value theorem. This is just going to be norm fx minus fx1 plus half norm x minus x1. Okay, so the net upshot of all this is that norm x minus x1 is less than or equal to twice norm f of x minus f of x1. Okay, so we just take half of norm x minus x1 to the other side and cross multiply this 2 and you get this. Okay, so what does this show? This shows that if y is sufficiently close to y1, then x is close to x1, because norm x minus x1 is less than or equal to twice norm f of x minus f of x1. This shows G is continuous. Right? The previous inequality actually shows that G is continuous. G, remember, was the inverse of f restricted to V. Okay, excellent. Now if we choose y such that norm y minus fx1 is less than r minus norm x1 by 2, suppose we choose y in such a way that y minus fx1 norm is less than r minus norm x1 by 2, then what happens is norm x minus x1 will be less than r minus norm x1. Okay, so if you choose y such that norm y minus fx1 is less than r minus norm x1 by 2, then norm x minus x1 will be less than r minus norm x1, which just means that this means that norm x minus norm x1 is less than r minus norm x1, where we have just applied this reverse triangle inequality. Okay, so what this shows is that we have shown that norm x is therefore less than r, just cancelling off the norm x once. We have shown that norm x is less than r. So what this shows finally is the fact that this shows this shows that W is open. Okay, this shows that W is open. So what have we actually obtained? What we have shown is if you choose the ball of radius r minus norm x1 by 2 centered at the point fx1, then if you choose any point y in this ball, then the corresponding pre-image x satisfies norm x less than r, which simply means that x is in V. So I skipped a step, I was a bit hasty. We have shown that norm x less than r, which means x is in V. X is in V. Okay, this shows that W is open because f of x equal to y is an element of W. Okay, so what is the net upshot of all this? W is also open. Okay, so we have achieved quite a bit. If you go back to the statement of the inverse function theorem, which was a long time ago, we have reached till the fact that this map G from W to V is a continuous map and it's a bijection. So we still have to prove that it's a C1 smooth map and also compute its derivative. Okay, so we have to show that G is differentiable. Okay, so let's show. We have to show G is differentiable, and in fact C1 and C1 smooth on W. Okay, now we have chosen long back, R such that the norm of H, which you recall was the map x minus f of x, this operator norm is nothing but I minus dfx operator norm is less than half whenever, I think less than or equal to half, I don't remember, whenever x belongs to B0R. This is the way we have chosen this R. Again, we had already concluded from this that dfx is invertible whenever x is in B0R. Whenever x is in B0R. Okay. Now, what is the objective now? We have to show that G is differentiable. So let y comma y1 be points of W and choose x comma x1 in V such that f of x equal to y and f of x1 equal to y1. Okay. Now our goal is to analyze g of y minus g of y1. Okay, and our candidate derivative claimed is nothing but dfx. So what we do is we subtract dfx inverse of y minus y1. Okay, so since the candidate derivative is dfx inverse, we subtract this and somehow we want to show that this is a sublinear function. Now by our choice of notation, this is just nothing but x minus x1 minus dfx inverse of x f of x minus f of x1. Okay, now we have to show that this entire term is sublinear. Okay, we have to show show sublinearity of the above term. Linearity of above term. In other words, what we actually have to show is we have to show that this whole thing divided by norm y minus y1 and limit y goes to, or y1 goes to y is 0. Okay, that's what we essentially have to show. Okay, now by the differentiability of f, by the differentiability of f, we can write f of x minus f of x1. This is the term that occurs as part of what we have to show. F of x minus f of x1, this is just d fx x minus x1 plus e of x minus x1. Okay, this is just coming from the differentiability of f, and e of x minus x1 is nothing but the error term. Okay, so what do we have to do? We have to now analyze this. So this gives x minus x1 minus dfx1 inverse. If you don't mind, instead of showing differentiability at the point y, I will show it at y1, because I said let's show differentiability of f at the point y, but y and y1 were arbitrary. So the way I have written it out, it makes more sense to do it at the point y1. So if you don't mind, let me just make a minor change. This is just x1 inverse, and this is just again x1 inverse. Okay, and again here also this is just x1 inverse. This is just x1, not x1 inverse. Okay, so this gives x minus x1 minus dfx1 inverse of acting on y minus y1 is equal to minus d fx1 inverse acting on the error term x minus x1. Okay, how did we get this? Well, x minus x1 minus dfx1 inverse of fx minus fx1, we just substituted this dfx1 x minus x1 plus e x minus x1 here, and then dfx and dfx1 inverse, both of these just cancel off, and you're just left with x minus x1 plus dfx1 inverse of e of x minus x1, which is what I have written here. Okay, right. So we have got this term, and we have to estimate this right hand side and show that the right hand side is actually sublinear, except the sublinearity we have to show with respect to the y variable. Even though it's written as if it's respect to the x variable, we have to actually show it with respect to the y variable. Okay, so what we have to show is this term. Let's take norm everywhere. So we have to show norm of x minus x1 minus d fx1 inverse of fx minus fx1. We want to show sublinearity of this. This is, by the previous line, less than or equal to the operator norm of dfx1 inverse times the error term x minus x1. Okay, now take y going to y1, take y going to y1. Okay, and we have, once y goes to y1, we have norm of ex minus x1 by norm y minus y1. This is less than or equal to 2 times norm of e of x minus x1 by norm x minus x1. How did we get this norm y minus y1 and relationship between this and this quantity? Well, some time back we actually showed this. I don't seem to find where. Yeah, here it is. We have actually shown this some time ago. So plugging that in, we actually get that norm e of x minus x1 by norm y minus y1 is less than or equal to twice norm e x minus x1 by norm x minus x1, and this goes to 0 because as y goes to y1, x goes to x1 by continuity of g, by continuity of g. Okay, so what is the net upshot? Net upshot is g is differentiable and the derivative dg at y1 is just df at x1 inverse, where f of x1 equal to y1. So we are almost done. Almost everything is proved. We still have to show that this map G is C1 smooth. To show C1 smoothness, we use that coordinate independent formulation of C1 smooth. We just have to show that the mapping y goes to dgy is continuous, where we treat the codomain as LE or LFE. So this is actually in LFE. In this case, it's just Rn and Rn. Okay, but what we have is this map dgy can be rewritten as d of f of g of y inverse. Okay, now G is continuous, F is certainly continuous, this whole thing is therefore continuous, and taking inverse is also continuous. Okay, so why is taking D here continuous? Because we have already assumed that F is a C1 map, and taking inverse is a continuous map. We have seen it long back. We have in fact shown that taking inverses when treated as a map on matrices is in fact a smooth mapping. We have already seen that when we did that example involving differentiating the inverse map. So DFGY inverse is in fact C1. This is in fact continuous map. This is a continuous map. Y going to this. So this shows G is C1 smooth. So all the part of inverse function theorem is now completely proved. So please go through this lecture carefully again, and please refer the lecture notes where everything is done in a way that you can actually refer back and forth. Because of technological limitations, I can display only a finite amount of mathematics on a given screen, and that is going to make the proof difficult. So what I'm saying in this lecture is just going to give you the basic idea of how this theorem is proved. It is up to you to now go through the proof line by line carefully in the notes so that you have a clear understanding of what is happening. This is a course on real analysis, and this was the long video on the inverse function theorem.